Good afternoon. It is a beautiful Monday, February 28th, and today we're looking at homework 3. Today's problem is a problem on dynamics and controls. We will be looking at a 3-tank problem, and we will be discussing flow rates, and also we will be solving for how Good afternoon. It's a beautiful Monday, February 28th, and today we'll be looking at homework 3. We'll be looking at dynamics and controls. We have a 3-tank problem today. All these 3 tanks are connected together, and we'll be looking at the flow between these tanks and how those different flow directions, values, and heights of the tanks can vary depending on the time and the flow. So, first things first, let's pull up our diagram. So, if we look at the chart, we see we have 3 tanks with cross-sectional areas. Cross-sectional areas, just add in our fluid levels here. Cross-sectional areas of the 3 tanks, so cross-sectional area of 1, cross-sectional area of 2, and cross-sectional area of 3. We see that those are 0.5, 1, and 2. Are interconnected at their bottoms with an initial fluid levels of 0.5, 1, and 2 again. So the level of tank 1 is 0.5. The fluid level of tank 2 is 1, and the fluid level of tank 3 equals 2. And it seems this does not want to go. Hold on. There it goes. Look at that. We see that the magnitude of the flow between the tanks is proportional to the square root of the difference in fluid heights between the pair of tanks. The proportionality constant between the tanks is 1 and 2. Between 1 and 2 and 2 and 3 are 0.1 respectively. And then tank 3 drains to the surrounding at a height of 0 with the same proportionality constant. So, what that is saying is that the flow between tanks 1 and 2, so the flow of 1 and 2 is equal to the proportionality constant times the height of tank 1 minus the height of tank 2. And that is squared. Notice it's an absolute value because you cannot take the square root of a negative number. And then same thing goes for tank 2, tank 2 and 3. The flow rate between tank 2 and 3 is the constant times the height of tank 2 minus the height of tank 3 squared in absolute value. And then it said that tank 3 had the same proportionality constant, 1.5. I seem to be running out of room. That is the proportionality constant times the height of tank 3 squared. No, square root. So then we come to the flow in. The flow into the second tank is set equal to the proportionality constant multiplied by the difference between the fluid level set point for the third tank and its actual fluid levels. So we can say the flow in is equal to proportionality constant times the tank 3 set point, so the height of 3 set point, or 4, minus the actual height of tank 3, which we don't know until we do some equations. So then we can say that the proportionality constant is equal to 0.1, because it says that right here, 0.1. Perfect. Alright, let's just make this full screen since we're done referencing that. There we go. Now, the flow rate between the tanks is dependent the sign of that is dependent on which way the flow is going. If one tank is more full than the other one, it will flow that way. If it's flowing backwards, it'll be negative, and if it's flowing forwards, it'll be positive. However, we can't determine that sign based on the difference in the tanks, because that always has to be positive since it is the square root. So we need to determine that based on the sign of the flow. So the flow of 1 and 2 is equal to the sine of 1 and 2 times the constant, and then the exact same thing. Same for flow between 2 and 3. This needs to be perfect. Okay, now the prompt that we are following here wants us to derive for the fluid levels in each tank. However, we're not going to do that exactly. We are going to relate the cross-sectional area to the change in height over time to solve for volume, and using those values we can find the height of the tank at any given time. So like I just said, cross-sectional area times dH over dt, or the change in height over time, is equal to the volume. So for tank 1, we can calculate that as cross-sectional area of tank 1 times the height of tank 1 over the change in time is equal to, since we only have one flow and is going out of tank 1, is equal to negative flow between 1 and 2. For tank 2, it's the same banana, except we have 3 areas of flow. We have the flow in, the flow between 1 and 2, and the flow between 2 and 3. Since the flow in is adding to the tank, and the flow between 1 and 2 is adding to the tank, those are both positive. So the flow in plus the flow between 1 and 2 minus the flow between 2 and 3. Since the flow between 2 and 3 is flowing to tank 3, it is leaving tank 2, therefore it is negative. And then for tank 3, again, same deal, except this time we just have the flow between tank 2 and 3 and then the flow out of tank 3. So then obviously between 2 and 3 is positive for tank 3, and then minus the flow out of tank 3. So like I said, we can use these equations to solve for the volume, and in turn solve for the height given the variable, given the given time. If that will zoom out for you, there you go. The next part, we will be putting all of this into Python, and we are going to make graphs so we can see what our tank heights are at any given time. Thank you.